Good morning, everyone. Today we are going to continue our talk about uh, material science review. This is our third time to review what we have learned in this semester. We have talked about this one. We have used the two class sessions to review previous parts. Now this is our third part of material science review, and we'll continue our talk. And we talk about the metals in last class, and then we talk about metal fabrication, several different methods there. And then we talk about thermal processing of metals, and how we already know we have hot working and this cold working. And the thermal processes we call heat treatment also. And annealing is one commonly used thermal processing with of metals. A heat treatment in which a material is exposed to an elevated temperature for extended time period and then slowly cooled. And be very, very careful. And elevated to the high temperature, hold for a period of time and then slowly cooled. Annealing is carried out for several purposes. One is relieve stresses because if we at the high temperature, um, residual stress will be relieved to some extent. And second one, increase softness, ductility, and toughness. And third one is produce a specific microstructure. And sometimes we want to have desired microstructure. Annealing consists of three stages. As I said, heating to the desired temperature, holding or soaking at that elevated temperature, and then cooling, slowly cooling, usually to room temperature, because we are usually using this kind of material at room temperature. So here is heat to the types of uh, annealing. Okay, first one is the stress release, and second one is spheroid dies to have the spheroid die microstructure. And third one is a full annealing and for steels, make soft steels for good forming and heat to get this is a gamma. A gamma is iron gamma, and then furnace cool to obtain coarse pearlite. Normalize and for steels, deform steel and with large grains, and then heat treat to allow recrystallization and formation of smaller grains, and to process annealing, negate these effects of cold working by recovery and recrystallization. So then we talk about ceramic crystal structures. We have talked about metal and metal alloys, and then we focus on the ceramic crystal and structures. Um, Ceramic, okay, you already have two different elements. They have this is the compounds. The cations, or usually the metallic ion, are positively charged. Iron, the non-metallic ions, usually they are charged negatively. And two characteristics of the compound ion in crystalline uh, ceramic materials include the magnitude of the electrical charge on each of these component ion, magnitude of the electrical charge, and relative sizes of the cations and ions. And because these two factors will determine the ceramic crystal structures. The crystal must be electrically neutral, okay? Because electrically neutral, that means can stable, and all the cations positive charges must be balanced and by an equal number of iron negative charges. So the chemical formula of a compound indicates the ratio of cations to ions, or the combination that achieves this balance. For example, calcium fluoride. We have one calcium atom and two fluorine atoms and ions. Now this time we call ions there because when give up the calcium gives up the electrons, and fluorine acquires the electrons. The metallic elements give up electrons when ionized. Cations are usually smaller than ions. So this is true for most of these metal atoms, metal ions. They are smaller than the counterparts of these non-metal elements. So each cation prefers to have as many nearest neighbor ions as possible. The ion also desire a maximum number of cation nearest the neighbor. So ceramic structures, and so there are several different ones. For example, rock salt. So this is a very common one. The sodium chloride is a representative, and calcium. This is a calcium. This chloride, zinc blend, fluoride, and this is a perovskite. So also this is spinel. So this is their names, structure names, and here is a structure, and here is this iron packing. So FCC, FCC, FCC. Also this coordination number, along with the examples here. And so this is the very important. Ceramic structures are very important for engineering applications. And so then we talk about the point defects in ceramics. We know vacancies, we know interstitials. So vacancies means that and supposedly there should be iron, cation or iron, but for some reason this guy is missing. So there is a vacancy. Interstitial, as the name suggests, and this is supposedly there is no this kind of cation or iron, but for some reason additional or extra cation or iron uh, is placed here. And so here is, for example, here is cation interstitial. You put one additional cation, and here is a cation vacancy. And so this supposedly this should have cation. Maybe that this guy just moved from this location to this location. So this is iron vacancy. Supposedly should have one to achieve perfect ceramic crystal structure, but for some reason this guy is missing. So this is iron and vacancy. And so Frankel defect. So cation vacancy and cation interstitial pair. So these are Frankel defects, right? So this is cation vacancy, cation interstitial. That means this guy is moving from the original the location where this guy is supposed to be to another location randomly or by some for some other reason. Another one is a Schottky defect, a paired set of cation and iron vacancies. These are vacancies here. So equilibrium concentration of defects, we use these two equations here. Okay, so and maybe you don't need to memorize these two equations, but I would suggest that and you know where to get these equations. If I give you this equation, ask you to solve the problem in the final exam, and you should be able to know where to get this Q, where it is a T, capital T, and also lowercase k. And this imperfection in ceramics, interstitial impurity atom. So this is impurity. This is different from the host atoms there, and this is substitutional impurity ions. So this is also different. And then we talk about the flexural tests for ceramics, and we use the flexural tests. Why? Because the tensile testing that is usually designed for the metal alloys, ductile materials, they cannot be used here because this is because ceramic is brittle, and if we apply the tensile stress, and it will break. And then we use this is the flexural testing, and so this is the sample. So there are two supporters, and we have one central force here, and we apply. So you can have cross-sectional, can have rectangular shape, or can have a circular. And so here is the delta is a midpoint, the deflection. And tensile tests are difficult for brittle material, as I said. So we use this 3-point band testing and to solve the problem. So determine elastic modulus and also the force, applied force along with this delta. So you can see here. So these are very similar to this tensile testing, but now this is a flexural. This we compress it. Okay, so this is a way when we calculate this is Young's modulus for rectangular cross-section area. So this one is for the circular cross-section area. So fractal strength and can also be calculated using this is a 3-point bending. And so these are typical values for the commonly used ceramic materials. Sigma fracture strength, fractal strength we call fracture stress when this is the the crack starts initiating and propagating. So here is the Young's modulus. So classification of ceramics, we have different kinds of. We have glasses, and we have clay products. This is corresponding properties. Refractories, abrasives, cements, and cements are very useful. Cements, right? So we use cements to build our houses, build our pavement, build our highway. A lot of good things. We use cements. Advanced ceramics, for example, engine rotors, valves, bearings, and also sensors. So this is the fabrication methods. And we have glass forming process and particulate the forming process and also cementation. Cementation is special, and we separate it, and we talk about this one separately. So this is a glass forming. We have pressing, blowing, drawing, fiber forming. Particulate forming, we have powder pressing. This particulate, as the name suggests, we have tiny particles. And hydroplastic forming and slip, this casting along with the tape casting. For here, hot, uniaxial, isostatic, and then we need to dry it. Then we need to fire it. We need to fire it. So to dry and fire to get the final products. So this is cementation. Cementation is special, and we will talk about this one separately. So then we talk about the polymer. Okay, polymer is a polymer multiple mer. Mer is a repeat unit. Poly is many in English language. So this is repeat unit. This is a polyethylene. This is a vinyl chloride. This is a polypropylene. So we have this one. This is very beautiful. I like this is repeat units, and we have repetition here. So polymer composition. Okay, most polymers are hydrocarbons. Hydrocarbons are commonly used, very common, commonly available these elements in the nature, in our on the earth, made up of hydrogen and carbon. Unsaturated hydrocarbon, each carbon singly bonded to 4 other atoms. So this is why we called saturated hydrocarbon. Right? Keep in mind, saturated hydrocarbon means that each carbon is singly bonded to 4 other atoms. For example, this ethane. So this ethane here, C2H6 and C. So we have single bonded. This C is single bonded. And double or triple bonded bonds somewhat unstable. For example, double bond. So this C has double bonds. Triple bonds. So this is triple. They are not stable. That means, and if there's some conditions available, and they will have the chemical reaction, which is not good, right? Chemical reaction is horrible for people's safety. As a molecular weight, the distribution, and we have based on the number and based on the weight, total weight of polymer, total number of molecules. This is number average, Mn, weight average, Mw. And so then we talk about ceramics of polymer um, molecules there, the characteristics, molecular characteristics, the chemistry, repeat unit, composition, size, molecule weight, shape, chain twisting, entanglement, etc. Structure, we have linear, branched, cross-linked network. Then we have isomeric states, and we have stereo isomers and geometrical isomers. For this one, we have isotactic, syntactic, and atactic. And this here is the sins and trans. So you need to know these words, okay? Know these concepts to know what this concept refers to, what is it talk about. And I might give you several conceptual the problems to solve, to answer, and in our final. And at that time, and don't tell me Dr. Ma has never ever taught you this. Do you have sense? I told you, I'm teaching now. Okay, so my bottom line is that you know what these concepts are talk about. And then we talk about thermoplastics and these thermostats, and they are different. Okay, so thermoplastics, little cross-linking, as the name says, plastic, ductile, soften with heating. For example, polyethylene, polypropylene, polycarbonate, and polystyrene. So thermostats, on the contrary, are significantly cross-linking, and hard and brittle, do not soften when being heated. And vulcanized rubber, epoxies, polyethylene, polyester resin, and phenolic this resin. So these are examples of the thermostats. So thermoplastics and thermostats, and they are very, very easy to be confused. One way I remember this, one way I differentiate these two similar concepts is that plastic means that it is easy to be deformed. Okay, so this is a ductile. And set, for me, we just say set is opposite to plastic. Set means this guy is hard and it's not easy to be deformed. So polymer formation. And there are two types of polymerization and addition or chain polymerization. And second one is called condensation step polymerization. So addition, we have a radical here, R. Initiation started, and this R, radical R, and forms a single bond, and with this is carbon. So as a result, this repeat unit and C is changed from double bond to single bond. Okay, propagation. Propagation means that here this radical moves here. Alright, then this radical will um, react with another repeat unit, and so these two CC, and they just form a new bond, single bond, and then this guy becomes stable, more stable. And so this is one step, and so on and so forth, and you will get a very, very long chain. And when it will terminate, so when this one C, okay, so these are, so this is a radical R, when these two guys, right, when these two guys, and R, so here is H, and C, and these are double bonds, and finally this is proportionation. So this is a combination. You combine them together, and then you have these CC. All these CC C carbon atoms, they are single bonded. So another one is a condensation called a step polymerization. So condensation, as the name suggests, we can guess, okay, and something happens here, and so this phenomena, and this we know that condensation means water comes, water appears, right? So here, so this is one, this H, this HO. So if these two gases are combined together, and they can form a new molecule, H2O, water. So this is the reason this kind of polymerization is called condensation. And then we talk about vulcanization, okay? And what is vulcanization? So vulcanization means the cross-linking process in elastomer is called vulcanization. And vulcanization means that with this cross-linking occurs. This is vulcanization, which is achieved by a non-reversible chemical reaction. You can see this chemical reaction, and ordinarily carried out at an elevated temperature. I will not read all these things, and you should know what vulcanization talks about. Vulcanization means cross-linking occurs at a certain temperature. So we talk about the standard EMF series. EMF here means electromotive, the force, and this series. F is a force here, but it is not the force. This is the volts here. Okay, these are volts here. EMF, and when you take the principles of mechatronics, when we talk about the motors, I will talk about EMF here also. EMF there also. EMF means electromotive, the force, and this is electromotive force. So this the series, as I said, this is called force, but it is the unit is the voltage. So you can see metal, and we have more cathodic, and this is more anodic. So this is commonly used the metals here. So metal with a smaller one corrodes. For example, CD nickel steel, and so this is a CD corrodes. Why this guy corrodes? Because this guy has lower EMF value. We also call it the potential. Um, So this guy will give up each of these atoms here, and they will give up 2 electrons. So these 2 electrons will come to another element. For example, here, so CD gives up 2 electrons for each atom, and these electrons will go and then reach here. So as a result, these nickel ions, and some of these nickel ions will acquire these electrons and become atoms. So this is nickel atoms will deposit on the surface. You can see. So this is additional the nickel atoms. On the contrary, here the CD. So this is we can have this is something. Some parts are missing. Why? Because so in this area the CD atoms, they give up the electrons and become ion. These ions, they dissolve in this solution. As a result, so here it's missing, right? So this is um, so this is corrosion. So here this corrosion in a grapefruit, and so here is the zinc anode corrodes. Okay, so this is a CO cathode, and here this is reduction reaction. I'm sorry. So cathode. So this is the electron. Okay, this is anode. This anode here. This anode 2 electrons come here, and then this is reduction, corrosion, and reduction, and they are the opposite. Okay, reduction means that deposition, and corrosion means that something are missing. So here, this guy corrodes, they give up electrons, and so they can become from atom that become the ion. The ion dissolves, and then here reduction reactions, they acquire free electrons and become a gas or become water. So there are two the possibilities. So then we talk galvanic series, wrecking of the reactivity of metals and alloy in seawater. So this one is very, very important, especially when we talk about when we work on these shipbuilding the projects. So this is more cathodic, this is more anodic. So forms of corrosion and stress corrosion and erosion corrosion, pitting, crevice, and galvanic intergranular, selective leaching, and uniform attack. So this is the forms of corrosion I want you guys to know and what they are, how they are different. So corrosion prevention, and corrosion is bad, okay? Corrosion is bad for our economy. And how can we prevent corrosion? We cannot eliminate the corrosion, but we can do our best to prevent the corrosion. And one is material selection. I use metals that are relatively unreactive in the corrosion environment. For example, nickel are in the basic the solutions. Basic it has a lot of OH, this ion. Use metals that passivate. I told you what a passivate is, right? What is a passivity? What is how it passivates? And these metals form a thin adhering oxide layer that slows corrosion. And the metal oxide, this metal, so this is adhering oxide. So this adhering oxide layer prevents oxygen to enter the component to cause further corrosion. So this is a very, very important adhering oxide layer. The lower the temperature, we know at high temperature um, corrosion is more active. Uh, so we can lower temperature, reduce the rate of oxidation and reduction. So apply physical barriers, and we can have physical films and coatings, and add these inhibitors, substance added to solution that decrease its reactivity. And for example, we can slow oxidation reduction reactions by removing reactants. For example, remove oxygen gas by reacting it with an inhibitor. So this is one very, very good way. Another one is a slow oxidation reaction by attaching species to the surface. That is called sacrificial material. So cathodic or sacrificial protection. So here, okay, so this is the attach a more anodic material to be one and to be protected to the one to be protected. For example, steel pipe, we want the steel pipe to minimize or to eliminate a corrosion of steel pipe, and then we use Mg here. Mg will be an anode, and then they just keep giving this is a free electrons to the steel pipe, and the steel pipe will not the steel these iron atoms will not lose the free electrons to become the ions. As a result, steel pipe and will not corrode. So the galvanized steel, zinc, this is zinc, galvanized this is steel here. All right.